Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to do the last example of moment distribution where we have a frame with a sway, meaning that if you have a load like a 10 kilonewton per meter here applied to the left column of this frame will start turning, right? There is a sway. There would be some kind of deflection at B and C. So in a case like that, how do we solve for the moments at the different supports? Well, in the first part, we would say something similar to what we did. Remember when we were trying to find the deflections in a truss member, and we said if there was no load applied, we apply a fictitious load. We'll do something similar, but not quite the same. We are going to say, okay, if I leave that load like that, there would be a sway in the frame. So what we are going to do is to say, wait a second, what if I add a pin or a roller, it doesn't matter, right here, like a fictitious support. Okay, let's say fictitious roller here. That would prevent the sway. So I'm going to solve for the moments, assuming I have a pin here, an extra pin, okay? And then once I find the different moments, I would use those to find the reaction at that fictitious pin. Okay, and then we are going to take all the loads and apply a moment. We'll see why as we go. And based on the moment or the moments that we are going to add, we are going to say, okay, what is the reaction due to this moment? So of course, it won't be exactly the same reaction as the one we found in part one. So let's say, just to make it easy, let's say the reaction I found in the first portion of the solution, after you add the roller, I get, say, 10 kilonewton. And then when I apply the moment, any moments, I would make up some numbers that are easy for me. And when we do these moments and we solve using them, we will get a different reaction. Let's say instead of 10, I got 5. So I would say, okay, so the moment, I will take the moments from part one and then add to them twice the moment from part two. Why twice the moment? Because in the second part, I said, suppose we got 5 kilonewton, and I know that it should be 10, right? Because the first part I got 10. So if I get 5, it says that the moment that I added to counter the effect of the load should have been multiplied by 2. We'll see that when we go through a whole example. So as we do, we are going to solve the first part. First of all, for joint B, I'm going to calculate the relative stiffness of AB to BC. So K, oh my God, that's a new pen because the other one. KAB as opposed to KBC. 4EI over L, and L is 4, so 4 over 4 cancel, but I don't have EI, I have 2 I's, 2 EI. If E is constant, I can ignore it. And as I said, I'm going to say this is 2 to 1. So we can say 4 times 2 over 4, because the length is 4. So 4 times 2EI over 4. And the other one would be just 4, because remember, these are fixed. 4, but it's only I, so times 1 over 4. So this is really 2 to 1, meaning 0.667 or 67 to 0.33. That's easy. Now let's do BC at joint C. KBC, which we said it's 1, right? To KBC Oh my God, this the length here is only 3, not 4. No, I'm sorry. This is 3. So while this is 4, the 4 and the 4 cancel and I get 2, 2 to 4 thirds. I'm sorry. 2 to 4 thirds, meaning if I multiply both sides by 3, I will get 6 to 4, or 3 to 2, or 0.6 to 0.4, right? 0.6 to 0.4. So let's write it here. It should be BA, not AB, right? Because we are at joint B. So this is 0.6 and this is 0.4. These are zeros because that's a fixed support. Then I'm going to do KBC to K, or KCB, actually, to KCD. As we said, this is 4 to 3, 4 times 1 over 3, to 1.5 times 4, which is 6 to 4. So if I take a common, this is like, okay, 3 to 2. 3 to 2. So if I take a common denominator of 6, that would be 8, and that would be 9. So 8 over 17, because they add up to 17. So 8 over 17, roughly 0.47, to 9 over 17, which should be 0.53. They have to add up to 1. So that's how we find the relative stiffnesses, 0.47, 0.53. Then we calculate the moments, right? So I'm going to say fixed end moment of AB, that would be negative W L square over 12. L is 4, so again, here you get 3 and 4. 40 over 3 is negative 1333. And FEMBA would be positive 1333 kilonewton meter. So this is negative 1333, and that's positive 1333, and there are no other moments there. Okay, so I'm going to do the distribution. Notice 0.6 and 0.4. So we are going to say 40 over 3, which is the 1333, times 0.6, but in negative. I will get negative 8. So that's negative 8. So that definitely would be negative 5.3333. So they add up to that, right? Then notice the carry over, the BA to AB, the BC to CB, and if there is anything in CB, would go to BC, and if there is anything in CD, it will go to DC. So these are the 4 types. In fact, I will never have 4 simultaneously, but these are the 4 carryovers that I have. The negative 4 will give me here negative 8 will give me here negative 4. That will give me negative 2.67. You like 67, I know. Okay, so I'm going to take this number and distribute it. So we can say 16 over 3, that's the 533, right? Times, divided by 2 to get the 2.667. And then I'm going to multiply that by 0.47. Notice that would be positive 1.25. That's good enough. And of course, the difference here would be 1.42, right? Now, the 1.25, half of it is 0.625 would come here, and 1.42, half of it would be 0.71 would go there. Let's do another distribution. So this is 0.625 times 0.6 in negative. That would be negative 0.375. And if I subtract this from that, I will get what? 0.25, negative 0.25, right? Did we get? Yeah. Yeah. So this will give me negative 0.1875. And that will give me negative 0.125. No, yeah, negative 1.25. Let's see, times points. Yeah, 0.6 and 0.4, correct. And this would be just the distribution of that. That's maybe the last one we are going to do. So if I divide this by 3, I will get that 0.125. So I'm going to multiply that by 0.47, roughly 0.059. And then 0.125 minus 0.059 would be 0.066. Okay, so we are going to calculate here the balance moment. I have negative 1333 minus 4 minus 0.1875. It's negative 1752. Negative 1752. Let's add those. 1333 minus 8 minus 0.375 is 4.96. 496, right? This would be, yeah, 96. Here I have negative 5.33 plus 0.625 minus 0.25. Again, it has to be the same, but we check for calculation error. Oh, I'm sorry, I'm not showing the calculator. I'm just checking all of them. I know they have to be the same, but if I had made an error, mathematical error, I can catch it if I don't get the same result. So for CB, the moment CB, negative 2.67 plus 1.25 minus 0.125 plus 0.059. And that would give me negative, I would say 149, right? If we use 2 decimal places, and then 142 plus 0.066, of course, it's the same. And finally here, it's 0.71. Notice I didn't do another carry over, but we could add 0.033, and that would be like 0.74 instead of 0.71. But the only reason I don't do that, because usually if I do a carryover for this, I would have done another carryover for that, and I wouldn't have a balance moment. So I would have to go through another like round. And it's the same thing on the others. I have to stop somewhere. So I prefer to stop at the distribution, not at the carryover, so that we have a balanced moment. Okay, so now my job is to find the reaction at the support. What is the reaction CX? Well, I can find AX and I can find BX, right? By looking at these two columns. So column AB, that has a load of 10 times 40 is 40 kilonewton, really. So the sum of these two has to be 40. I'm not really worried about BX. They didn't ask me to solve for all the internal loads to draw the shear force diagram and the bending moment diagram. So I only need the reactions. The moment at A is negative, meaning it's going counterclockwise, 1752. But the one at B is positive, meaning it's going clockwise, right? 496. And I had, oops, I have an AX here. So I'm going to take the moment about B. This one is going clockwise, so I'm going to move it to the other side. I'm going to calculate the clockwise as positive. No, the counterclockwise as positive and the clockwise as negative. So when I rotate here, I have 1752. Then I have minus 496. And then I have 4 times 10 is 40 times 2 is 80, so plus 80. And then I divide by 4, so I get 2314, right? This is 2314. I will do the same thing for CD to calculate DX. At CD, I have a moment, a clockwise moment of 149. And here I also have a clockwise moment of 0.71. So I'm going to add these two and divide them by 4. 149 plus 0.71 equals 2.2 over 4 is 0.55. That's why I did. No, I'm sorry. This is the opposite direction, right? Because this is rotating clockwise, so that has to rotate counterclockwise. It's 0.55. So now summation of the forces in the X for the whole frame equals 0. I get 40, which is the distributed load, minus 2314 plus 0.55 equals 1741. So that has to be 1741 kilonewton. 1741. Now, when I go to the second part, and I already redrew those, let me make these 0.6, 0.4, 0.47, 0.53, and 0. Now, how do I find the fixed, it's not a fixed end moment, but the moment that I will be using in part 2. If you remember what we did with the slope deflection method, when we were calculating, when we said you do 2 EI times twice theta, the close one plus theta, the far one minus 3 psi, which was delta over L. So really, we are going to add moments on these two legs, positive moments on these two legs, based on the ratio of their EI over L square. Why over L square? Because remember, it was 2 EI over L times twice theta, say A plus theta B minus 3 psi, which was delta over L. So really, the E is the same. The delta would be the same. It's the same thing. I don't have rotation because I'm fixing the support. It's like I'm keeping them from rotation. So really, and delta is the same. So basically, it's and the 2 is the 2. So I can just look at I over L square. So the ratio of the I of this leg, in fact, it's 2I. So 2I over L square, which is 16, to wait a second. What did we say? I'm sorry. Did I say this is 3 delta over L? So this is L square. It should be I square over L. So here, what is the ratio? but it's the same L. So really, yeah, it's the same L. So it's the ratio of 2 to 1.5. That's all. Pens. 1.5 L I over 16. Again, the 6, I don't care about the 16. It's 4 to 3. So I can pick any moment of my choice, right? You can take some easy number, like, for example, I can make this is 30 and this is 40, or maybe that's a 90 and that's 120. So I end up with, some people would always pick one of them to be 100. So for example, if I pick this as 100, this would be 75, or this is 100 and that's 133, 33, whatever. So let's pick any number. It really doesn't matter. The most important thing is the ratio. So I can say, for example, notice this one is the bigger one. So I can call this this is 100. So it would be a nice number. And this is 75. So I'm going to say 100, 100, 75, 75. So to both legs, you add uh, just a moment, a positive moment. Okay. Positive moment, meaning I'm going clockwise and clockwise, because that's what would do the sway of the 10 kilonewton. It will go in this direction. So anyway, and here we don't have moments. So we will start. That's easy. The 100 would be negative 60 and negative 40. And the 75, maybe we could have made that 100 would be easier because we are multiplying by that ratio. 75 times 0.47, I get 35 and a quarter, so negative 35.25, and 75 times 0.53 is 39, negative 39.75. Now, notice, now I have a carry over here, I have a carry over there, I have a carry over here, and I have a carry over there. So all four of them. This would be negative 30. That would be, let's say, negative 20. In fact, it's negative 19.875. I don't know. We can, okay, 875. I don't want to mess it up. The negative 40 would be negative 20, and this guy would be negative, again, 17.625. So 17.625 times 0.6 is 10.575. And 17.625 times 0.4 is 705. Half of that will go here, 5 point. Again, we can say 288. Yeah, if 3 decimal places is more than enough. Let's do this first. This would be 9.4, and that would be 10.6, right? 2 times that, it's easy. Then we are going to do this would be 4.7, and this would be 3.5. Let's make it 5.3 or 5.2. Previous time we increased, so let's decrease it. Or we can use 3 decimals since we used here 3 decimals. Okay, 2 point. Alrighty, so the 4.7 times negative 0.6 is negative 282, which would bring here negative 141. And 4.7 times negative 0.4 is negative 188. The 3.525 times negative 0.47, again, we'll have to approximate here. So negative 166, and 3.525 minus 1.66 is negative 1.87. If we, yeah, they will have to be some kind of approximation anyway, and this would be point or negative 0.94. Then again, half of this will go here, negative 0.94, and half of that will go here, negative 0.83. And then I'm going to go up another distribution. So the 0.83 times 0.6 is 0.5. So 0.5 and 0.33 roughly. And the negative 0.94 times 0.47, that's twice much as that, 0.44, and this is 0.5. So this will give me 0.25, 0.25, 0.22, and 0.165. And the last distribution, the 0.22 times 0.6 is 0.132. Negative 1.32, and times 0.4 is negative 0.88. 0.165 times negative 0.47 is negative 0.078, and 0.165 minus 0.078 would give me negative 0.087. And I'm going to stop here. Okay, let's calculate. So here 100 minus 30 is 70. Plus 5.288 minus 141 plus a quarter. So we are going to approximate that as 74.1. Here I have 40 plus 10,575 minus 282 plus 0.5 minus 0.132. Of course, we are going to approximate, so 48.1. Here, check to make sure we get something close to that, negative 40 minus 17,625 plus 705 plus 40.7 minus 188 minus 0.83 plus 0.33 plus 0.22 minus 0.8. That's 83, not 88, by the way. Half of that is 0.0. In fact, 0.0. Oh, no, I'm sorry. No, that's correct. That's correct. Minus 0.88. 48.9. Oops. Wait a second. Let me check something quickly. 17,625. These add up to that. These add up to that. These add up to that. So I should get them right. So we said 40 plus 10 minus 2. Let me check quickly. Plus 0.5 minus, so that's correct. Let me check this. Maybe I did something wrong. Negative 4. That's why I prefer to check. I mean, the difference is not that large, but still, it's not. what I expected that to be. Plus this, plus that, minus 188, minus 0.83, plus 33, plus 22. That's interesting. 8.9. Let me see. Yeah, I did something wrong. I'm sorry. This is, as I said, this is 0.088. 48,123, so negative 48.1. That's why I prefer, as I said, to check. Sorry, guys, should be more careful. Minus 20 plus 9.4 plus 3.525 minus 166 minus 0.94 plus 0.44 plus 0.165 minus 0.078. It's negative 44.4. No. Okay. Yeah, here I didn't see the 75. Minus 39.75 plus 10.6 minus 187 plus 0.5 minus 0.087, 44.4. Okay. And the last one I have 75 minus 19.875 plus 5.3 minus 0.94 plus a quarter is 59.7. Okay. Now we are going to repeat what we did before to find the reaction here, except that this time we don't have loads, we have just moments. Okay, so let's do it here. So I'm going to draw AB. Here is element AB. The moment at A is positive, meaning clockwise 74.1. And at BA is also positive, excuse me, so it's also clockwise 48.1. So the reaction here would be to the right, the sum of these divided by 4. 40, so between parentheses, it's better, 48.1 plus 74.1 divided by 4, I get 3055 kilonewton. Then I'm going to take CD. The moment CD is again 44.4, and this is 59.7. Both are positive, so I'm going to add them again. Okay, so between parentheses, I'm going to say 44.4 plus 59.7 divided by 4. And again, this is 26.025. So the reaction at C is the sum of these two. Do you see that? I have a reaction to the right, a reaction to the right, and a reaction to the left. And because the sum of the forces in the x equals 0, this has to be the sum of these two, because in this case, I don't have the distributed loads. There is no external load. There are just moments. So I'm going to say this plus that. So this would be 56.575. That's how we are going to find all the moments. I'm going to say MAB equals the one we found from before, which is negative 1752. And then I'm going to take the ratio of the actual reaction over this hypothetical reaction. meaning I want to decrease the moments produced here by this ratio. So I'm going to say plus 1741 over 56,575 times the moment I found here. So I'm scaling it down by the same ratio of the actual reaction that I would have found had I had added a roller here over the hypothetical reaction, because I didn't know what the actual moments are. So I just made up some numbers that are easy for me to make the calculations. And then I would say, oh, but I shouldn't have 56. I should have only 17. So let me take all these moments and reduce them by that ratio and add them to what I had before. So basically here, what I have is negative 1752 plus 1741 divided by 56.575 times 74.1. And that gives me 528. Okay. So the moment here is 5.28 kilonewton meter. Again, notice that we have made some approximations, not much, but these are very close to the actual moment. MBA equals, the original one was 496, but then now I'm going to add the same ratio, 1741 over 56,575 times 48.1. And that would be 496 plus 1741 over 56.575 times 48.1. And I get 1976. I should get the same thing here for BC. BC, the moment is, so I'm going to take the same number. Of course, since I'm using, oops. Okay, I'm going to insert a negative because it's a negative 4. And then here also, this is negative 48.1. So when I multiply, I'm going to add, notice that I'm going to insert a negative sign. And of course, I should get the same exact result, negative 1976. So again, there is no reason to do that since I already know I'm using the same numbers. I'm just changing the signs. So negative 1976 kilonewton meter. MCD would be negative 149 plus 1741. Let's say 471. I don't know where I got that. Divided by 56,575 times negative 44.4, right? So I get negative 15.15. So MDC, no, I'm sorry, this is MCD. MCD would be the same, but positive, right? Because same number, but in positive. So there is no reason to repeat the same calculation. And finally, MDC would be 0.71. That's what I had before, plus 1741 over 56,575 times 59.7 equals 0.71 plus 1741 over 56.575 times 59.7. It gives me 1908 or 19.1 kilonewton meter. And that's basically it. So when you have a sway in the frame, it's like it's as if you are solving two problems. You solve a problem as we did before, the same exact one, but then you add fictitious moments at the same ratio of I over L square. If the i's are the same, you will have the same moments. And you would say, oh, I forgot to tell you. Of course, we add the moments to the columns. Why? Because these are the ones that will sway. BC will not happen. BC will just move. Okay, it's not gonna happen anything to it, but this line would go like that, and this column would go like that. That's why we add the moments to correct the vertical, or to tell us exactly what would happen to the vertical columns. And we add the moments based to the ratio of I over L square, I over L square. But since the i's, the L's are the same, it's just I to I. 2 to 1.5 is the same as 4 to 3. So you pick any two. I could have picked 40 and 30. Any ratio, it doesn't matter, because at the end of the day, you are going to normalize it back and say, oh, that shouldn't be this number. It should be 17.41. So all the moments that you find here, you are going to either, in this case, scale them down, or if I had used 3 kilonewton meter and 4 kilonewton meter, I would have scaled up, because definitely the reaction would be smaller than 1741. But at the end of the day, you are solving the same exact method. The only thing is that you are adding these fictitious moments and calibrating them so that you get the same reaction, and then boom, you add the two moments to get the final moment. I hope it wasn't that bad. If you have any questions, again, don't hesitate to ask, and I will come back to you as soon as I can. Otherwise, I wish you all the best and hope to see you soon. Bye.